Next, we will see about the bound magnetization currents. When a magnetic material is exposed to magnetic field, so basically the magnetic dipole moment can be produced, okay, by using these three factors. First, the electron orbit around the nucleus, the electron spins, as well as nucleus spin. So these three conditions will create something we call as a dipole moments. The unit is ampere meter square. So what happened is actually the moving electron produces a small bound current we label as Im. In magnetic material, dipole moments align the atom in uniform directions. And then we can define the magnetization vectors M is equal to magnetic dipole moments per unit volume. So we have a lot of magnetic dipole moment in a certain volume of our magnetic material. So we can define the magnetization vector M equal to N dm ampere per meter. So where N is equal to number of dipole moment per unit volumes. Let's see these two conditions. First is a condition without external field. So you can see that the dipole moment is random. Okay, it has a lot of directions. So in this case, the dipole moment is not equal to 0. It has a certain value, but the magnetization is 0. For the second case where we applied with the external field BA, so you can see that the dipole moment started to arrange in the certain direction, the same direction. So in this case, the magnetization is not equal to 0. It has a certain value. Alright, please consider this figure. Imagine if we have a lot of dipole moments in our magnetic material and is arranged in such a way it can produce the magnetizations. Okay, so when we analyze this kind of structures, we can find that there is something formed in the material we call as a bound surface magnetic currents. The symbol is a JSM. Is defined as a magnetization cross product with a unit vector normal to the surface, and the unit is also the ampere per meters. And then we have the bound volume magnetic current, where we define the bound volume magnetic current Jm is equal to the curl of M, and the unit is ampere per meter square. If the magnetic field inside is uniform, so basically the Jm is equal to 0. Right, so hopefully you can imagine what happened here, because the case is really identical with what we analyzed for electric field. Okay, this is the direction of our external field. So this is a dipole moment arranged in the same direction and create a magnetization vectors. Let's see another figure. Right, so consider this figure. Let's say you have a lot of dipole moment inside the magnetic material due to the external magnetic field B. So the dipole moment will arrange in the same direction, therefore it will create the magnetization vectors. From the figure, the bound magnetization surface current density is formed on the surface of our magnetic material. So the JSM equal to magnetization cross product with the vector normal to the surface. So each surface will have a different normal vectors. And inside the magnetic material, we have maybe the bound magnetization current density, where we can find which this expression, the Jm equal to curl M. Because this is a curl, involve the vectors. So basically, if the M is if uniform, it only have a constant value. So basically, the Jm will become 0. So the M should be in the form of variable or non-uniform, right? As I mentioned here. Okay, let's see another figure in 2 dimensions. So we have a lot of dipole moments, okay, inside our magnetic material. So it is uniform due to the external magnetic field. Let's see in detail what happens. Okay, we have a dipole moment arranged together, and if we analyze at the boundary between the two dipole moment, we can see that the current loop will always cancel each other at the boundary. Let's see in this part. We have the current going up, and then the neighboring dipole moment will going down. So let's assume it has the same magnitude, so it will cancel each other. It's the same with another boundary here and here. So as a conclusion, basically what happened if it will create the bound surface magnetic current only on the surface of the material. So there is no other current inside. Let's see the further analysis on magnetic field inside the magnetic material. Originally, we have the curl H equal to J. This is the original, the Maxwell equations. For the magnetic material, we have to add another Jm. So the bound magnetic current density, the Jm. So we extend further, where the H is basically equal to the B divided by mu naught. It's equal to J plus Jm equal to curl M. And then we can bring the curl to be in the left hand side. So we have here the curl B divided by mu naught minus magnetization is equal to J. So this one is basically originally is H. Okay, in the bracket is H. So H equal to B divided by mu naught minus M. Right? So inside the material, the field current and bound current combine to produce internal field. Okay, basically the magnetization will contribute to the internal field B. So as a conclusions, the magnetic field inside B is basically equal to mu naught H plus M. We have another which is magnetizations. So originally we have the B equal to mu naught H on the free space or in vacuum. So we have to add extra magnetization for magnetic material. Okay, further analyze these expressions. So B is equal to mu naught H plus M. If we can change the M into the psi M H, where psi M equal to susceptibility, so we can change this expression into B equal to mu naught H 1 plus psi M. And we define later on the 1 plus psi M to be mu R, the relative permeability. So the expression can be simplified into two. B equal to mu naught mu R H. When we change mu naught mu R equal to mu permeability of the magnetic material. So the final expression can be simplified into B equal to mu H. Next, we go to material classification. This is very important because normally you will be asked during the final exam about this. Maybe you need to see further on this. We have a three material classifications based on their permeability. First, we have diamagnetic, where it almost nil dipole moments, or the mu r is almost equal to 1. We consider diamagnetic as a non-magnetic. For example, the helium, hydrogen, inert gas, bismuth, sodium chloride, copper, gold, silicon, germanium, sulfur, and so on. Where for this case, the internal field is less than the external field. The next material is what we call as a paramagnetic. So these are random small moments. Mu r is also almost 1. It still have the magnet effect, but it's very weak. For example, we have a gallium, oxygen, rare earth elements, and so on. In this case, the internal field is greater than external field. It's just slightly greater. The third material is what we call as a ferromagnetic. This is a very important. The ferromagnetic has a large moment and also the large mu r. We consider the ferromagnetic as a strong magnet. For example, iron, nickel, and cobalt. For this material, it has a large internal field even after the external field has been removed. That means when we expose this kind of material with the external field, after we remove it, it still gives the magnetic effect.